Good afternoon, viewers. Welcome to Noble UK Academy. This afternoon, we will be discussing thermodynamics. And the area we'll be looking at is actually OTTO cycle. Looking at this question, we have the minimum pressure and temperature in an OTTO cycle are 100 kilopascal and 27 degree, meaning that the minimum pressure we have here is this P1, and then the T1 is this. The amount of heat added to the air per cycle is 1,500 kilojoule per kilogram. Now the question says, determine the temperature and pressure at all points of the air standard OTTO cycle. Of course, OTTO cycle is known as constant volume cycle. Now you have something of this nature. I'm gonna draw my PV diagram, and you must be able to master this. My PV diagram comes in this format. I have my constant. This is a sharp curve. All right, I'm gonna call this is my compression from here to here. It's my compression. Okay, I can label it as 1, 2, 3, 4. Okay, if you want to describe what happens when you are making use of a steam turbine, the working principle of a steam turbine, I could draw it in this format. Here. Heat outlet. Then you have feed pump, and then you finally have this. Okay, this is my boiler. This is my reheater. This is my turbine. Okay, this is my feed pump. Of course, the pump sends water, pumps water. At this place, you have pressure. Pressure is coming from the pump, and the pump sends water into the boiler. The boiler heats it up and transfers to the reheater. The reheater works on it, further exerts pressure on it, heats it up, and then it's gradually turned into steam. And then at this point in time, it is no longer normal water, it has become vapor, and it is brought down to the turbine as a steam. It is the steam that opens up the turbine, and the turbine further works on it and transfers heat. The compression we're talking about here, and then transfers it back here, and the whole process starts again. The cycle starts all over again. So that is what we are trying to describe here using PV diagram. Okay. Now mind you, this is described as constant volume diagram. Constant volume cycle. This is an OTTO cycle. Another word for it is constant volume cycle. Okay. Now, this is what happened under gas power cycle. Okay. Now, having described this, we are told that the first pressure and the first temperature happens to be this and this. Okay. Meaning that our P1 is equals to 100 kilopascal which is something like what 100 times kilo is 1000, okay, Pascal, which will further give 10 raised to power Pascal or Newton per meter square. Another unit for Pascal is Newton per meter square, and this 500, let me call it Newton per meter square, okay, is same thing as 10 raised to power 5 Newton per meter square will give you 1 bar. The same thing as 1 bar. 1 bar, right? Bar is a measure of pressure. Another unit for pressure. Okay. Now we are told that our first temperature T1 is equals to 27 degrees Celsius. So we're going to convert it to Kelvin. We become 27 plus 273 Kelvin. And this will amount to, that should be 300. Yes. This will give us 300 Kelvin. That is to say 273 plus 27. This is 10 carry 1. This is 9 plus 1. 10 right 1 carry 1. That is 300. Okay, so we're still on the same page. That's 300 Kelvin. Okay. Now, at our compression region, this is a compressed region. We have one between 2 to 1 or 1 to 2, between 1 to 2, which is T2 over T1 gives us our compression. Our compression, that is R. And this R is same thing as, mind you, this is constant volume. Meaning that if I trace this thing down here, this is volume. Our volume is constant, meaning that V2 is equals to V3. Okay? So our compression here is equal to V1 over V2. Sometimes you can use V2 over V3, then our compression ratio. So this is equal to the same thing as this R. So I'm going to have gamma minus 1. Okay? So if that be the case, it's further broken down as T2 over T1 is equals to V1 over V2 minus 1. This is what we're going to be having. Okay. Now, what is my T2? T2 is not known yet. What is my T1? My T1 is 300. Okay. Is equals to my compression ratio from the equation here. The compression ratio is 8 over 1, which is 8. 8 divided by 1 will give you 8. So we have 8 all over. Our y here is from the equation 1.4. And that is 1.4 minus 1. Okay? So this is what we're going to be having. Okay? Now, I'll clean this off. From the cycle I described with a diagram which I've cleaned off, we find out that from this point 1 to 2, the piston is actually compressed. Now coming down to this place, boiler takes it up and then transfers pressure. Then coming down to here, you have isentropic expansion, which is heat also. Heat is equally added at this point. Between 3 and 4, you have heat addition. Meaning that if you have to get the amount of heat that is added, it's going to be CV into bracket T3 minus T4. Okay? That is our heat addition. Heat addition. Okay? But we are getting there gradually. Now, I'm going to have T2 is equal to 300. That is if we cross multiply. Becomes 300 into bracket 8 raised to the power 0.4. That is 1.4 minus 1 will give us 0.4. So T2 further becomes 300 into okay, let's simplify 8 raised to the power 0.4 and see what that is going to give us. Let me open up my calculator, my power calculator. It's a scientific calculator. Okay, 8 raised to the power 0.4 gives me 2.2974. 2.2974. Okay, so my T2 further becomes, multiply this out. Okay, 2.22974 multiplied by 300. This gives me 689.2 Kelvin. Okay, let's just say 689 Kelvin approximately. That is for T2. Okay, and if you have P1 V1 Y is P2 V2 Y. Okay. This will further give me P1 over P2 is equal to V2 Y. Okay. Instead of going through these rules, I could bring P1 down and then take P2 up so that I can still maintain my compression ratio. So this becomes P2 over P1 gives me V1 over V2 or gamma. Okay. So, on the look of things, we're now gonna have P2 over P1, which is 1, is equal to, mind you, my P1 is 1 bar. Okay, is equal to the compression ratio, which is V1, V2 is something as compression ratio all over 1.4. Okay, so P2 becomes 1 times 8 raised to the power 1.4. Okay, so my P2 becomes, let me check out the value of 8 raised to the power 1.4. Okay, that is 18.38 bar. That is for P2. That is for P2. Okay. That is that for P2. We will still go on and on to get the value of our P3, T3, and the rest. Okay. So if being the case, I'd rather say T3, T2 will give me V2, V3, all raised to the power 1 minus 1. Now we've gotten P2, that is the second pressure. We're now gonna look for our T3. We've gotten T1, we've gotten T2. Okay. So it is at this process 2 to 3 that we'll be able to get our T3, because that is where heat was added, heat was introduced, and that is process 2 to 3, and that process 2 to 3 is called constant volume. Constant volume. You can see the volume is constant, just a straight line. 2 to 3, the volume is constant. 2. Okay. Now at that point where heat was added, that is heat addition. At the heat addition region, we have CV into bracket T3 minus T2. Okay. Heat addition. Sorry, it's T3 minus T2, not T4. T2 in between 2 and 3. Okay, the process is between 2 and 3. So we have that at this point where our heat was introduced is between T3 and T2. Okay. And mind you, we'll already be given the amount of heat that was added, which is what? 1,500. So we have CV into bracket T3 minus T2 gives us 1,500. That is the heat addition. Okay? So now our specific heating value is from the equation is actually 0.718. Okay? Then into bracket T3, we've not gotten T3, minus T2, we've gotten T2, which is 689. Okay, close the bracket, is equals to 1,500. All right, now multiply this out. This multiplied by this will give us the same thing, which is 0.718T3 minus this multiplied by this. That will give, I think, 494.5. Then it will be 195 approximately. Let's check it out. This is my power calculator. 0.718 multiplied by 689. Okay, that is 494.7. Then approximately 495. Okay, let me still maintain the decimal value here. Let me still maintain it. I have this multiplied by this give me 494.7. Then is equals to 1 half. Okay, what do? I collect like this one move to this side. I have 0.718T3 is equals to 1,5. This one moving to this side become plus 494.7. So I have 0.718T3 gives me, let's add up. Still open my power calculator. This is 1,5 plus 494.7. That will give me this 1,994.7. Okay, that's 1,994. 1,994.7. What do? We divide both sides by the coefficient of this, which will give me. Okay. This goes off. I'm left with T3. T3 has now become. We divide the whole of this by 0.718, and that gives 2,778. 2,778. This is 2,778 Kelvin. That is our temperature at this region. Okay. Now, having gotten all of this. Lest I forget, our T3, because I want to clean up the board. Let me just write down the parameters that we have limited board space. Our T1 from what we got in T1, I've cleaned it up. Yes, our T1 was 300 Kelvin. Our T2, from what I've generated, 689 Kelvin. Our T1 was 1 bar. Our T2 was, I think, 18 point something bar. Yes, 18.38 bar. Okay, and then our T3 now. T3 is 2778. Okay, that is that like the way. So I want to rub off this. This side should I rub off? Okay, let me rub off this side. Now, after getting this, we're gonna look for our T4. We've gotten T3. We're gonna look for our T4. Mind you, T3, T4 is equal to V4, V3, all raised to power minus 1. Okay, mind you, this is still compression ratio. So this further gives 200 and our T3, 2,778, 2,778 over T4 had become our compression ratio, which is 8 into Y minus 1, which is gamma minus 1, which is 1.4 minus 1. Okay? I've cleaned up the diagram. I would have shown why this place is equally considered as a compression ratio, but it's off already. Now we have 2778 all over T4 is equals to 8 raised to power 0.4. This is 0.4. Okay. All right. Now it further becomes that T4 is now equal to 2778 divided by 8 raised to power 0.4. Okay, our T4 has become 2778 divided by 8 raised to power 0.4. I'll open up my power calculator. 8 raised to power 0.4 will give what class? 2.2974. Okay, 2.2974. This will give 2.2974 approximately. So our T4 becomes, let's divide through 277. Okay, that gives 1,000. Now more so during the constant volume, that is from stage process 2 to 3, we also have that T2 P2 is equals to T3 P3. Okay, so at this point it becomes obvious that our T2, that is 689 over P2. What's our P2? 18.38. Okay, is equals to T3. Our T3 is 2,778. Okay, all over P3. We've not gotten P3. Okay, so if we cross multiply, our P3 becomes 18.38 times 2,778 all over 689. So P3 automatically becomes 18.38 multiplied, can see from my power calculator, multiplied by 2,778, okay, gives this, then divided by 689, okay, that is 74, approximately 74 bar, okay, that is 74 bar, approximately, yes, 74 bar approximately. Now under adiabatic expansion process, we have that P3 V3 raised to power 1 is equals to P4 V4 raised to power gamma. Okay, and that is gamma. Okay, now following this process, our P3 V3 becomes okay. Yeah, becomes V4. This should be P3, sorry, P3 P4. P3 P4, or we can take it as P4 P3, okay? P4 P3 becomes V3 over V4 is all raised to power gamma. Why do I have to do this? If you multiply this out, we are getting this back by simple calculation.